All right, Chapter 7 Review, Part 2. Here we go. Let's get after it. These are all word problems. Exponential growth, decay, and then some half-life type problems. So population in 2020 was approximately 7.8 billion. So that's our initial amount. That's our starting amount. The annual rate of increase was about 1.05% worldwide. So write an exponential function to model the population. So the population is, we got y equals, now we put our initial amount, so 7.8. I'm not going to write out all the numbers for billion. We'll just know our answers in billions. Now our increase, we had an increase of 1.05%. So it's always 1 plus the percentage. But 1%, if I just said, hey, what's the decimal for 1%? Well, that's 0.01. But 1.05%, I just added the 0.05 to the back. So it's actually going to be 1.1.5, not even 1.5, 1.05%. And then X is the number of years after 2020. So there's my generic equation. That's my start. So use it to estimate the population in 30. So to find the population, I do the starting amount, the growth rate, and in this case, if we went from 2020 to 2030, that was 10 years. So I'm going to do this to the 10th power. And when I put that in, I got 8.66 billion. So 8.66 billion people. All right, so that's in 10 years. Now, use logs to find the year in which the population is going to reach 20 billion. So I need to find the year. So I'm trying to figure out t for this one. But I know our final amount. All right, this is the final amount, is 20 billion. So I know the start, I know the growth rate, I know the finish, but I don't know the exponent. And we're going to use logs to solve this one. You could use a graph, but I want to see you use logs to solve it. So here we go. So I end up with 20 billion. Right now we were at, 7.8. I know my growth rate, but we need to figure out the X part, how many years. Now you could graph the left side, graph the right side, both for Y, find out where they intersect, or go to a table, but I want you to use logs. So what I'm going to do is, in order to use logs, I have to get the base by itself. I just need the base and the exponent on one side. So I'm going to divide by this 7.8 from both sides. And that's going to cancel out. So over here on the right, I'll have just the base and the log, which is what I need. On the left, I'm going to have a decimal. I think I changed that down to 2.5641. I usually keep about 4 decimal places with these problems. You really should keep it as a fraction, but I've been letting you guys just kind of do this. We're just learning. And now, once I have it down to where I have to solve an exponential equation, I'm just going to take the log of both sides. I could do the natural log if I wanted to, but I'm going to just do the log and do the log. And once I do the log of both sides, whenever you have a log expression, you are allowed to put this exponent right here. This exponent is allowed to move to the front. So I'm going to put that exponent in the front, and then I'm going to have, the times the log of 1.0105. And over on this side, I still have the log of 2.5641. And now to get x all by itself, you're just dividing by this log from both sides. And of course, you're going to have to go to a calculator because I don't think anybody has those logs memorized. But whatever those are, that's my answer. So let me punch in. Actually, I have it written down right here. I'll save some time in the video. And it comes out to be about 90 years. So X is about 90 years. But it says find the year. So if our initial value, this initial value was in, I believe, 2020, all right? And then we're going 90 years later. So you're talking like, 2110. 2110 would be the year we expect to hit 20 billion people on this earth if growth continues to stay the same. the growth in the world is actually declining. Population growth is actually going down worldwide. Actually, I know in the United States, I'm pretty sure in actually the world, though, I think our growth rate was a little higher than one previous. Anyway, here we go, number 2. Computer valued at $4,500 appreciates at a rate of 15.2% per year. So a couple things you need to do. Change this to a decimal. So that's going to be 0.152. Remember, you just move it 2 places or divide it by 100. So for this problem, I started at 4,500. My rate of decline, I'm depreciating, I'm going down. So I got to do 1 minus 0.152, which is actually 0.848. All right, when I do 1 subtract 15.2%, I get 0.848. And to the x power, so there's my function. Find the value of the computer after 3 years. So they're giving me my x, they're giving me my time component. So I'm just going to punch into the calculator. I started at 45. We're less than 1, so we're dropping for 3 years. And when I put that in my calculator, I got roughly 27.44 and 10 cents would be what that is worth. And that comes into play for like businesses. Businesses can write off depreciation of their equipment. So they, there's usually like a standard amount for different types of technology or heavy equipment that's acceptable for their tax people to kind of look at and write off as depreciation of new equipment, or older equipment, I should say. All right, number 3, population of an animal species. Again, we are decreasing, so we're going down. So decrease is going to be 1 minus the percentage, and the rate is 3.5. So as a decimal, move it 2 to the left, that's 0.035. So there's going to be my decrease. I counted 80 at the moment. So my model is going to be, my initial value is 80. We are decreasing. So I got to do 1, take away that amount. If you lose 3.5%, that means you're at 96.5. And this will be my t or my x, whatever you want to call it. Use a graphing calculator to estimate the number of years until the population first drops below 15. So I want to know, when is y? When is this value over here? At what t? I got to find that t. Now, if we were using logs to solve this, I could divide both sides by 80, take the log of both sides, move t to the front, do everything I did in number 1. But I want to see if you can do it on the calculator. So I got 80 and 0.965. So check this out. I pull up the graphing calculator, and we'll move it out of the way just a little bit here. And fire this bad boy up. Y equals, clear it out. So 80 times 0.965 raised to the x power. And I'm going to go to a table. So I could graph it, and then I could put 15 in here if I wanted to. I'm actually going to go to a table, though. So I'm going to go second table, and let's just check out these values. Now, right now, I have it at 0.1. I think this said go to the nearest year. So I'm actually just going to go in here, and I'm going to change my table set from 0, and we're just going to go by regular ones. And let's go back and check out that table. So we start at 80. We are dropping. Remember, I'm looking for 15. So when do we go below 15? Getting closer. Oh, crap. Where'd my calculator go? Fire back up. I'm almost there. Bear with me. Right there. So it looks like from year 46 to 47 is when I dropped. So the nearest year, I'm going to call it 47. So t equals 47 years, and we will be down to only 15 animals left. All right, moving on down. Number 4, this one's kind of interesting. Thought I'd throw it in here. A ball is dropped on a hard surface from a height of 25 inches. So kind of visualize this. We have this, you know, kind of table up here, and we got this ball, and the height starts off at 25. And then what's going to happen is it's going to come down and it's going to bounce, boom, and it's going to come back up to 2/5 of its height. So not quite halfway, all right? So 2/5. So one thing you might want to think about is, if I kind of broke this thing up into 5s, you know, maybe 1, 2, 3, 4, 5. 2 of those 5, that would be right here at about 10. So just kind of know, like, after my first bounce, this ball is going to bounce back up, and it's going to stop right there after one bounce. Now, you could just keep playing the 2/5 game and keep breaking it down, and doing a picture. Maybe I'll do it one more time. So if I go 2/5 of 10, you know, what is 2/5 of 10? Well, if I break 10 into 5 parts, that means every part would be 2, right? So if I broke 10 into 5 parts, and I'll get rid of this line because that's kind of right in the middle, but let's break 10 down into 5 parts. So 1, 2, 3, 4, 5. 2 of those 5, well, that's going to put me at 4. So after my next little bounce, boom, I'm going to come back up. So I've lost a lot pretty quickly, all right? You know, this was bounce number 1. Bounce number 2 got me up to 4. And I want to kind of figure out what's going on here. And eventually I want to get down to like 1 inch. So let's kind of start setting up our equation to think about this. So y equals my starting height, this is my initial height, was 25. Now we are losing, we are decreasing our height, all right? And if we're only at 2/5 of our original height, all right, that's 0.4. So I'm only at 0.4 of my original height, all right? Or I've lost 3/5. I've lost 60%. You know, so I could do 1 minus 0.60, or I could say I didn't lose 60%, but I'm only 40% of what I used to be. And so times every single x, which is x are the number of bounces. So we're trying to figure out how many of them are going to be less than 1 inch. So when is this going to be down to 1, basically? So we need to solve that equation. We could punch that in our graphing calculator, and we could see when we go below 1. I can kind of look and see right now over here, if I just play this game one more time, and I kind of play the 2/5 game, if I break 4 up into 5ths, which is kind of tough, 1, 2, 3, 4, 5. If I divide 4 by 5ths, that's 0.8. So these are each going to be 0.8s here. So it looks like if I do 2 of those, my next bounce coming down, you know, I go for my third bounce, I'm only going to go up 2 of those 0.8s. And that's going to put me at 1.6. And I think the next bounce, that's going to put me lower than 1. So after the 4th bounce, I never get back to 1 inch. But let's look at it on a graphing calculator. So let me pull that bad boy back up. So let's go to y equals starting height 25. I am at 0.4 or 40% height each time, raised to the x power, and lock it in. Go to my table, and let's table set because I'm still down at 42. So let's start back at 0, going by ones. So second table. And you look right here, after 1 bounce, I'm at 10, 2 bounces 4, 3 bounces 1.6. After the 4th bounce, I only get back to 0.64. So my rebound is going to be less than 1. My rebound is only 0.64. So the answer for this one is 4, whoop, I'm still in baby marker, 4 bounces. After 4 bounces, I don't rebound. All right, let's get rid of that one. I thought that one was cool. It's a little bit different, kind of a physics problem. My boy Rob would like that one. He likes the chem ones too. Bacteria culture containing 200 bacteria doubles every 3 hours. So you have this bacteria in a petri dish. It's doubling every 3 hours. So I can write an exponential equation for that. I got y equals, I'm starting at 200. I'm doubling, so we can just put a 2 there, every 3 hours. So I got to think about this a little bit. If it's every 3 hours, and I got a little typo here. This little typo should be like let t. It's supposed to be an italics t. Let t represent the days that it grows. So I'm going to put this up here to the t, but if t is my number of days, that equation is only going to grow once per day. I'm growing every 3 hours. So 3 hours, that's going to be 8 times each day. You know, my bacteria is going to double 8 times a day. So I need to have 8t there. That was kind of the tricky part of this one, because you want to do it how many times it does in a day. And then it says, what's the count going to be after 2 days? So basically y equals, start with 200, I double, and I double 8 times a day times 2 days. I could have just wrote a 16 there. So this is going to be a giant number. You know, we're talking 200 doubling 16 times. And when I put it in my calculator, I got a pretty big number. I got 13,107,200. All right, 13,107,200. All right, let's move on over to the back page, see what we got going on in here. All right, back after it, number 6, it says you received $2,500 in gifts at your high school grad party. You decide to put the money in the S&P 500 index fund. So I looked this up. It said the fund is an average return of 11.1% compounded annually. That was over the last 50 years. Some years you do great. You make 40, 50%. Other years you lose your butt. Like this year right now, the stock market's not doing too good with everything going on in the world. But if you're young and you're going to do it over a long period of time, you can usually assume a certain percentage. So we're going to assume 11.17% interest. How much will your investment be worth in 12 years? So the formula for compounded annually, 1 time per year, that's what that means. You take the amount, and then you have P, which is your principal, your starting amount, and we're growing. So this is going to be 1 plus R is my interest rate. And T is how many years are we going to do this for? So I want to know how much is it going to be worth. So we don't know what A is. That's what we're missing. Our principal is our starting amount, $2,500. Now my growth rate, 11.17% as a decimal, R is going to be 0.1117. But I have to add 1 to it. So in my parentheses, I'm going to have 1.1117. And then I have to do the number of years, which was 12. So I was thinking, hey, if you're 18 and you want to just tuck this money away for a little bit and not mess with it, we'll see how much you have when you're 30 years old. So I pop this in here, and I'm like, all right, 2,500, 1.1117 to the 12. I got $8,908.23. So, you know, you've between 3 and 4 times your money by not touching that. Now, just for giggles, I'm going to punch in here 2,500 times 1.1117. And let's just do something crazy like 50 years. So say you want to take it out at 68 years old. Be like, man, what's that grad present worth now? You'll be pretty amazed. If you put that in there for 50 years, so you just said, I'm not touching my grad money till I'm 68. At 68 years old, you would have close to $500,000. You'd have $498,104. That's pretty amazing to go from $2,500 to almost $500,000 by not touching it. If the S&P 500 kept doing what it's historically been doing the past 50 years. Pretty cool. Always invest early and keep putting a percentage in there every month. You'll be very happy as you get to retirement age. You never think you can afford it, but just do it anyway. You won't miss it once you get used to it being taken out of your paycheck. All right, hospitals use technetium-99 in imaging scans of the skeleton and brain. This isotope has a half-life of 6 hours. Find the decay constant. I believe that, and I don't know, I think on our other sheet ours had 30.1 hours, but how I find the decay factor, it's pretty much the same every time. We are going to have half of our amount, half of the full amount, so we're starting with 1, we end with a half, e to the negative kt. So there's my equation I'm always going to use, and what's going to change when you're finding this factor is they give you the t. They tell you the half-life for the different isotopes. So I'm going to put 6 right there for t. I'm going to clean this up a little bit. I'm going to change this to a decimal. And 1e is just e. And that's going to be a negative 6k, because I put 6 in for t and kind of moved it to the front. So I have this equation now we have to solve. So every equation you're going to solve kind of looks like this. Then you have to find the natural log of both sides, all right, which is really nice because the natural log and the e cancel out. And so now I just have the natural log of 0.5 equals negative 6k, divide both sides by negative 6. And you will see that k equals, and I crank this decimal out, and I got 0.1155, and then there was some other stuff. I think it was like 54, what I have, 5301. But I usually if I keep like 4 of them, I'm in pretty good shape. So that's our decay factor. That's our constant. That's k. I'm going to need that to do the other parts of this problem. All right. So now let's start figuring out, either, hey, how much is left after 20 hours? Or they tell me the hours and they want to know how much is left. So let's go down and let's do part B. The initial supply needed for this imaging scan is 100. So I know I need 100. And I need to use logs to find the amount that remains. So I don't know this side. I don't know how much remains after 72 hours. So this is going to be 100e to the negative, and we determine what k was. So here's where I pop in this k number, 115. And we're trying to figure out after 72 hours. So this is going to be my t up here. So luckily this one, I don't really have to even use logs because all I need is what's on the left. I can just jam all this crap into my calculator. And when I did it, I got down to 0.0244 grams. So hardly any is left. So after 72 hours, this particular isotope or this chemical, it's gone. Like there's hardly nothing left. And I wasn't really sure about that number. I was like, yeah, that seems kind of weird. Like that's pretty small. But if you start with 100 and you start chopping it in half, if the half-life is every 6 hours and you're going to 72 hours, you're having 112 times. So if that's at 0, if I half it once, this would be after 6 hours. Half it again, that's 12 hours. Half it again, that's 18 hours. Half it again, that's 24 hours. I still have a long ways to go to get to 72 hours. So that's why it becomes so tiny when you get down here all the way to 72 hours. So sometimes it's helpful to make a little chart just to kind of see. All right, part C, how long will it take the 100 milligrams to decay to 5? Well, I saw on my chart we were down to what, 24, and we were at 6. So not going to be too far after 6, but let's go ahead and let's either use our calculator or use logs. So I want that 100 to get down to 5. So this time I know the start, I know the finish. It's e to the negative, I know the growth or the decay factor. But this time we don't know t, how long. So I'm trying to figure out this t part. So a couple different ways you could do it. You could graph both of these and look at the table. So that would be one option. Just graph y equals 5. You know, graph y equals this part, graph y equals this part, see where they intersect, or just check the table until you get to 5. I'm going to use logs though, just because that's what we've kind of been doing. So I'm going to divide both sides by 100 because I have to get the base by itself. So I do that, and I get 0.05 equals e to the negative 0.1155. And if you've done enough of these, you'll start to see that, you know, we take the natural log of both sides. This goes away. And basically it just equals what's over here. And to get t, I divide both sides by that growth factor. So divide both sides by the growth factor. And I ended up getting, when I worked that out, 25.93 hours. 25.93 hours. Which that jives with earlier, because earlier, I think on our table at 24 hours, we were down to 6.25. So we were going to get to 5 very quickly, because another 6 hours would have got me to 3.125. So 5 would be a little bit closer up here. So that 25.93 makes good sense. Always want to use your BS meter when it's all said and done. All right, looking at number 8, find the decay factor. We've done enough of these. Pretty much, I can just get really fast here. It's going to be the natural log of 0.5 over the negative half-life. Like, that's what's going to happen. If you look at every other single problem, by the time you natural log both sides and move things around and cancel out the e, and the exponent comes down, then you divide by what's beside t, you're going to be left with right here. This is going to give you k. And so when I do this one, I end up getting 0.0396. So there's my decay factor. And then we come down, and it says how much is going to be remaining after 70 days from a 90 milligram sample. So I don't know the amount remaining, but I do know I start with 90. It's e to the negative kt. K was 0.0396. We knew it was going to be 7 days. And I pop that into my calculator, boom, boom, boom. And I get 68.21 is the amount left. So we're going to have this many milligrams after 7 days. And that makes sense because the half-life was 17 days. So if you think about it in a chart, 90 milligrams at 0 days, well, at 17.1 days, we go down to 45 milligrams. We get cut in half. But I wanted to know what happened only after 7. So I'm going to be actually closer to 90 than I am to 45. And this looks like it would work. All right, so I believe that takes us to the end. Hopefully this helped you with some word problems, get you ready for the test. See you.